At the beginning of this chapter, we saw that our objective was ultimately to represent functions as power series. But before we could do that, we needed to pick up a lot of vocabulary and understanding about the basic algebra with respect to infinite series, which is what we've been doing with all the sections involving series convergence tests, and including the section on power series with intervals of convergence and radius of convergence. So we finally have enough theory to begin representing functions in general as power series. So how are we going to do this? Well, we're going to be looking for bridges. Bridges from the universe of functions to the universe of power series. And at the moment, we really only know one bridge. So let's recall. If the absolute value of r is less than 1, then this particular series here converges, and its sum is a over 1 minus r. So we're going to use this as our first bridge from the universe of functions to the universe of series. And the way we're going to do that is we're going to let a equal 1 and r equal x. So we can now say that 1 over 1 minus x is equal to this infinite series. Okay, note that this is a geometric series with a equal to 1 and r equal to x. So given that it's convergent, its sum would be a over 1 minus r, or 1 over 1 minus x here. Writing it out in terms of its terms, we would see this is 1 plus x squared plus x cubed plus x to the fourth, etc. And these are both provided that the absolute value of x in this case is strictly less than 1. So when I say this is a bridge, what I mean is we have a function that's in the form of functions that we know how to deal with, and this is literally equal to this infinite power series. So how can we use this to write other functions as a power series? Well, let's look at a quick example. Okay, so we have the function 1 over x cubed plus 1, and we want to write that as a power series. Well, we can use the bridge via this geometric series by writing 1 over x cubed plus 1 as 1 over 1 minus negative x cubed. So it's kind of in the form of 1 over 1 minus stuff. And we know that 1 over 1 minus stuff converts over to the infinite series of that stuff to the n. So in this case, it'll be negative x cubed raised to the n. Okay. Well, it's always a good practice when you have a bunch of stuff raised to the n in the context of series to distribute that exponent. So what we really want to write here is negative 1 to the n, x to the 3n. And if you wanted the terms of this series, we could see that that's plugging n equals 0 in. We get 1 minus x cubed plus x to the 6 minus x to the 9 plus etc. Okay, so this here in sigma notation is a power series for this function right here. And of course, these are the terms of that power series written out. We also were quickly asked to find its interval of convergence. So we can see that the interval of convergence is the set of x values for which this is true. Well, you could just go ahead and do the ratio test on this like we've been doing in the last section. But we also know that going from this step to this step is only valid if this expression here, which is the absolute value of r, is less than 1. Well, that only occurs if x is strictly between negative 1 and 1. Or you could write it as an interval. Okay, let's also express this function as a power series and find its interval of convergence. So again, it is reminiscent of the form 1 over 1 minus x. So what do we want? Well, we want a 1 here, don't we? Not a 3. So what we're going to do first is factor a 3 out of the denominator. And let's also rewrite the order of these terms. So we have 1 plus 2/3 x squared. Okay, well, we also want a 1 here in the numerator. So this is more like 1 over 1 minus x. All right, well, let's just factor x over 3 out of this entire thing. So we have x over 3 times 1 over 1, and we'll even change the plus to a minus negative 2/3 x squared. So now we have some stuff, who cares, times 1 over 1 minus stuff, right? And that's the form we wanted, because now we can say, well, this is x over 3 times this infinite series of this stuff here to the n. All right, so we just need to clean this thing up. Again, let's distribute the n into every single factor. So we have negative 1 to the n, 2 to the n, x to the 2n, and this is all over 3 to the n. And you can see one of the reasons why we do this is that we're going to have to move this x over 3 into the series. And it's really easy to do that because each factor is individually raised to an exponent. So we're going to have here our 2 to the n, and then we've multiplied x to the 2n by x. So that's going to be x to the 2n plus 1. And we've multiplied in the denominator 3 to the n by 3. So this will be 3 to the n plus 1. And this here is a power series for this function. All right, here it is written, of course, in sigma notation, but if you want the terms of this power series, you can plug n equals 0, n equals 1, etc. into this. And what would we get? We would get initially x over 3. And then when we plug n equal 1 in, we would get negative 2 x cubed over 3 squared, which is 9. And then plus 4x to the 5 over 27, and then minus 8x to the 7 over 81 plus So for x values in the interval of convergence, this function is identically equal to this series with these terms. Actually, we were asked to find the interval of convergence, so let's quickly do that. Again, if you've used the geometric series, as we did to bridge over, it's very easy to find the IOC, because this step is only valid if your sort of absolute of R value, which would be this guy here, is strictly less than 1. The other way to do this would be, of course, just to apply the ratio test directly to the series, as we were doing in the last section. So here, we can see that absolute value of negative 2/3 x squared must be less than 1. So, of course, this means that x squared must be less than 3/2. And that means that x must be between negative rad 3 over 2 and positive rad 3 over 2. Okay, let's go to Desmos and see if this actually makes any kind of sense. All right, so here we have our function x over 2x squared plus 3 graphed. And let's turn on this series. Now, of course, Desmos, again, it's not smart enough to handle a series up to infinity yet. So we have to do the partial sum up to capital N, and currently capital N is set to 0. So this is actually just the first term of this series, which is the line y equals x over 3. And you can see it is tangent to the function at 0. And as we drag the capital N slider to the right, we're going to look at more and more partial sums, and we're going to get even better and better polynomial approximation of the original function. So you can see this is n equal 3, and then we keep going, and it's conforming more and more to the curve, although it seems to not have any interest in conforming to the curve outside of these particular bounds, negative something up to positive something, where it glues itself to the curve and then just flies off to infinity or negative infinity outside of these bounds. And of course, these bounds would be the interval of convergence that we found. So let's quickly just plot those two as vertical lines. So we had on the left this point, x equal negative rad 3 over 2. And you can see that that's sort of the left end of where the series wants to conform to the function. And of course, if we add the right endpoint of the interval of convergence, we can see that our graph completely agrees with our findings from before. So there it is. All right, so we're going to continue basically doing the same thing. But here it's not so obvious how to write this in terms of 1 over 1 minus stuff. However, it does say to write it as a sum of power series, so that gives us a bit of a hint on how to proceed. And we're going to use partial fraction decomposition. So I'm going to omit the details of partial fraction decomposition because we know how to do that, and that's not the focus of this example. But it is true that this expression is equal to this particular sum. And that's excellent news because both of these guys are in the form of 1 over 1 minus stuff. Well, this one almost is. We just need to factor 1/2 out of this entire expression. So let's quickly do that. We have 1 over, we might as well write this as 1 over 1 minus negative x. And this one as 1/2 times 1 over 1 minus negative x over 2. All right, so what do we have here? Well, this one is this particular series, and this one is 1/2 times this particular series. Okay, so we just have to clean this up. Over here, we distribute the n to get negative 1 to the n, x to the n. And here, we're going to distribute the n and bring this 1/2 inside, which will combine with the 2 in the denominator within the sigma. So we're going to have n equals 0 to infinity of negative 1 to the n, x to the n, and it would be 2 to the n, but there's one more factor of 2 down there, so this will be over 2 to the n plus 1. And there it is. That's our final answer. Okay, well, what about this one here? 1 over the quantity 1 minus x squared. So let's first take the naive approach, which is going to turn out to be incorrect. So don't take notes on this part. Okay, this is true, and we know that this inside part here is equal to n equals 0 to infinity of x to the n. So that quantity is being squared. Now, nothing's wrong with what we've written. However, this is not the form of a power series that we want. And it's certainly incorrect to distribute this as x to the 2n, which is a very common mistake, but that's not even mathematically correct. If you really wanted to force this into the form of a power series, you would have to recognize that this is the product of this series with itself. Of course, that's what it means to be squared. And that would be these terms multiplied by these terms. And you'd actually have an infinite foiling job to do. Now, there's actually a way of doing this and getting the right answer, but it's beyond the scope of what we're interested in for this class. And we have a much better way of dealing with the original power series than pursuing this particular dark path. So let's back up and try something different. Now, here's a wonderful fact. Calculus can be applied to power series term by term, and moreover, the radius of convergence will be preserved when you do this. So what the heck do we mean by calculus can be applied? Well, since we have the following, 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x to the fourth plus which of course in sigma notation we know is this, then you can take the derivative of the power series term by term, and the equality is preserved. So taking the derivative of the left-hand side here, 1 over 1 minus x, we know that's 1 over 1 minus x quantity squared. And we can now take the derivative of all the terms on the right-hand side. So the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. Derivative of x cubed is 3x squared. And the derivative of x to the fourth is 4x cubed. All right, and we could even take the derivative within sigma notation here. So the derivative of x to the n is nx to the n minus 1. Okay, but there's no reason for this particular series to start at n equals 0 because the 0th term of this is 0. So the correct way to write this would be n equals 1, nx to the n minus 1. You also could have just literally done this term by term without sigma notation at all, and then considered what we have here and wrapped it into sigma notation based on simply assigning this as n equals 1, this as n equals 2, this as n equals 3, this as n equals 4, and you will see the pattern is nx to the n minus 1. If you insist on starting this at n equals 0 and you prefer to have an x to the n, you simply do something called shifting the index of summation, where we reduce the initial index by 1 and we add 1 to all the n's within the actual sigma. So this is going to be n plus 1 x to the n. And you can see that this series will generate the same terms as this series, which are these terms here. Okay, so we've answered the question, because the original question was to express 1 over 1 minus x quantity squared as a power series. Well, we did that, and we did it via calculus. Okay, so here we need to find a power series for this big old thing. Well, let's start with the geometric series form that it's most similar to. So if we kind of strip away all the detail, let's start with this guy. 1 over 2 minus x. And again, if we want to just find the power series for that, we want a 1 right here. So we can factor 1/2 out, and we have 1/2 times 1 over 1 minus x over 2. And that we can bridge over to the universe of power series because it's equal to this. So distributing the n and also bringing this 1/2 in, we get x to the n over 2 to the n plus 1. Very good. So what do we really want? We want like this thing sort of cubed, and we also want an x in the numerator, or an x cubed in the numerator even, but we'll worry about that toward the end because that's actually not going to be that hard to deal with. So let's take a derivative, and actually we're going to take 2 derivatives in order to get that cubed down here. So we'll take one derivative at a time. So the first derivative of this thing is this. Okay, so we'll take the derivative of this expression here, and we're going to get that the derivative of x to the n is nx to the n minus 1, and this is just a constant. So we don't do anything to the 2 to the n plus 1. Remember, it's a derivative with respect to x, not with respect to n. All right, and we're not quite done because the first term of this series is 0. If you plug n equals 0 in, you just get 0. So we might as well start this, and it's good practice to set that equal to 1. So the first term of this will be an actual non-zero number. Okay, well what we really want is this denominator to be cubed. So we're going to have to take another derivative, and that's going to do the trick, isn't it? Okay, this time the derivative of stuff to the negative 2 is negative 2 stuff to the negative 3. Of course, chain rule would cancel the negative as it has been. So we're going to get 2 over 2 minus x cubed for that derivative of the fraction. And on the right, we're going to take the derivative of this expression, which really just means the derivative of x to the stuff. So the n minus 1 will come down. We get x to the now n minus 2. And this is all over 2 to the n plus 1. Okay, and just like last time, we can see that the first term of this new series is going to be 0 when we plug n equal 1 in. This factor will equal 0. So we might as well set the first index of the series to be 2. And in fact, this is pretty standard. If you produce power series through this derivative process, the first index of the series will typically match the order of the derivative. So this is a second derivative, n equals 2 down here. Okay, what do we want? We want x cubed over 2 minus x cubed. So we have to get rid of this 2 and replace it with x cubed. So we can get rid of the 2 by dividing everything by 2 on both sides. So that, of course, creates a new factor of 2 in the denominator. So instead of 2 to the n plus 1, it's now 2 to the n plus 2. And finally, we're going to get the form that we're after, because all we have to do is multiply both sides by x cubed. Now, we could write x cubed times stuff, and then in the next round, just bring the x cubed in. But let's just do that right in one step. So multiplying x to the n minus 2 by x cubed means we're going to add 3 to the exponent. So the n minus 2 becomes n plus 1. This is over 2 to the n plus 2. And there we are. We have found a power series representation for this function. Okay, so what about this one here? Well, let's recall that we worked out earlier that this particular form is equal to this series here. And its terms are 1 plus 2x plus 3x squared plus 4x cubed plus etc. So what does that mean? That means that if we multiply both sides of this equality by x squared, we're going to get this form. And let's multiply these terms by x squared. Now, a lot of the time, it's easier to work directly with the terms rather than the sigma notation, and just defer the sigma notation until you're done with the whole problem. Sometimes it's easier to work directly with the sigma notation, sometimes directly with the terms. So just play around with whatever feels right for you. Here, I'm working directly with the terms. So we're multiplying each term by x squared. Okay. Now, also, if you look at the original form of f of x, we have x over 1 minus x quantity squared. So let's write out a series for that as well. And we're going to get that by multiplying all of these terms by x. Okay, so why are we doing this? Well, f of x, which is of course just the sum of these things, is going to be the sum of all of these terms. So this is actually pretty easy because we only have one x, and then we only have 2 terms with an x squared, and 2 terms with an x cubed, and 2 terms with an x to the 4th, and so on. So we just add them. Here, x squared plus 2x squared is 3x squared. 2x cubed plus 3x cubed is 5x cubed. 3x to the 4 plus 4x to the 4 is 7x to the 4. And then we can see we're going to get 9x to the 5, etc. So we've done all the work term by term, not in the sigma notation. However, we're ready to put our answer in the form of sigma notation. And to do that, all we have to do is just consider the pattern that we have literally right here. So let's just start at n equals 1, and we can see that it's going to be something x to the n. Well, what is that something? Well, the pattern is 1, 3, 5, 7, 9. So these coefficients are always 2n minus 1. So there it is. Okay, let's find a power series representation for the natural log of 1 plus x. Well, there's certainly nothing algebraic that will connect this with the bridge that we know, the geometric series form of 1 over 1 minus x. But of course, we're only one calculus move away from that form. For instance, we can say that ln of 1 plus x is an antiderivative of dx over 1 plus x. Now, there is a constant involved, but let's just suppose for the moment that the constant is wrapped up inside the integral. So this is the sum n equals 0 to infinity of negative 1 to the n x to the n dx. Now, typically, when you're integrating a power series, it's a lot easier just to do this term by term. So let's write out the terms of this power series. We're going to see we get 1 minus x plus x squared minus x cubed plus x to the 4th, etc. dx. And now we can integrate each term. So the integral at this point will generate the constant, and let's put the constant first so we don't have to worry about it. And 1 integrates to x, negative x integrates to negative x squared over 2, and then we have plus x cubed over 3 minus x to the 4 over 4 plus x to the 5 over 5, etc. And you can also see why we put the constant in front, because it's a little weird to have plus dot 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 and then plus a constant after that. All right, now before we wrap this back into sigma notation, we do need to handle the constant. The constant is not just an arbitrary constant. It's a specific number associated with this series, because ln of 1 plus x is a function that evaluates to a number when you plug something in for x. So we have to determine the constant at this point. So we have to choose an x value to plug into both sides of this equation that will help us find capital C. So just look at the series and ask yourself, what x value can we plug in that will eliminate all the terms? And in this case, and in many cases, that is simply x equals 0. So on the left-hand side, we're going to get ln of 1 plus 0. And on the right-hand side, we're going to get c plus 0 minus 0 plus 0 minus 0. So we can see, of course, that c is equal to 0. So our conclusion is that ln of 1 plus x is equal to the following power series: x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus dot dot dot. And in sigma notation, it's typically written like this. We could determine the interval of convergence of this power series to be negative 1 to 1, including the 1. And in fact, by letting x equal 1, we get the very interesting result that ln of 2 is equal to 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus etc. The alternating harmonic series adds up exactly to ln of 2. Okay, well, what about this one here? So, well, we know that ln of 1 plus x is equal to a specific power series. So all we have to do is make this thing kind of look like ln of 1 plus stuff. Yeah, so how do we do that? Well, let's factor a 7 out. Now, we can't factor the 7 all the way out of the log, of course, but we can within the log here. We can write ln of 7 times 1 minus x over 7. And now we can use the properties of logarithms to write ln of 7 plus ln of 1 minus x over 7. Let's actually write that as 1 plus negative x over 7. And that makes our intent very explicit because we have ln of 1 plus stuff, right? We know what to do with that. So we have ln of 7 plus n equal 1 to infinity, negative 1 to the n minus 1. And then instead of x to the n, we're going to write negative x over 7 to the n, and this is all over n. So this is the form of ln of 1 plus stuff. And our stuff here is just negative x over 7. So yeah, all we have to do is clean it up. Okay, so we'll distribute the n into all of these pieces. So we're going to get negative 1 to the n, x to the n, and this is all over n times 7 to the n. Okay, well, what's the story here with these negatives all multiplied together? So we have negative 1 to the n minus 1 times negative 1 to the n. Well, if we add those exponents, we're going to get negative 1 to the 2n minus 1. It doesn't matter what n is, this exponent will always be an odd number. So this is always an odd number of negative 1's being multiplied together, which is simply negative 1. So we can say this is ln of 7, and there's a single negative 1 factor, which we can just pull right out and say it's just minus all of this stuff, like that. Okay, so that's our final answer. Now, I want to point out that it's not the only final answer. In fact, a function can have many power series representations, and some of them can look quite different from other ones. Let's look at another way we might approach this. So again, we want to bridge this over using the fact that we know how to convert ln of 1 plus stuff, right? Well, why don't we just write this as ln of 1 plus 6 minus x. So now it's in the form of ln of 1 plus stuff, and of course no one would disagree that this equality holds here. So what would that give us? Well, that would give us this. N is equal to 1 to infinity of negative 1 to the n minus 1, and then that stuff, which is 6 minus x to the n, all over n. Okay, now first of all, this is a perfectly valid power series. It's a little non-standard the way it's written, because if we're going to have something other than simply x to the n, we would really like to have it in the form of x minus a to the n. Right? Remember the definition of a power series back in the last section. So to get that, we need to extract a negative 1 to the n out of this form. And now we can write it as x minus 6 to the n as desired. Okay, but we're back in this situation where we have negative 1 to the n minus 1 times negative 1 to the n. So last time we knew that that simply collapsed to a single negative factor, so we can actually just write our series this way. And you can see that whole endeavor was worthwhile because this form is a lot cleaner and more descriptive of the situation than this form here that we were in danger of leaving it as. Okay, so these are two fundamentally different correct answers to the question, find a power series representation for ln of 7 minus x. And we're going to get into detail on these distinctions in the next section, but let's take a look and see how they each manifest graphically. Okay, so this red curve graphed is y equals ln of 7 minus x. Let's turn on the first series that we found, and of course, at capital N equal 1, this is only the first partial sum. So we have, in this case, looks like a linear approximation. And if we, of course, increase the partial sums, we get it conforming to the curve. That's all well and good. But notice that the point of tangency, which is most obvious when we have the linear approximation, occurs right at x equals 0 in this case. That is because this series here is centered at 0, in the sense that we can think of this as x minus 0 raised to the n. If we investigate the other solution that we got, so let's turn this one off and this one on, we can see that the point of tangency occurs at x equals 6, and that's because this series is centered at x equals 6. So a series is always centered at the a value where you have x minus a, and that's one of the important reasons why we want to write a series in the form of x minus a number, or just x by itself if we're centered at 0. Okay, so if we drag the slider to the right and increase our capital N, we get more partial sums, and you can see the series slowly conforming to the logarithm over there, centered at 6. You might think, well, gee, the other one was better because it conformed over a wider interval of convergence, and indeed it does. If you work out the intervals of convergence for each one, you're going to see that the first solution has a wider interval of convergence. That doesn't mean that it's better than the second one, because we might be interested in the behavior near 6, in which case we really ought to use this series, which is centered at 6, and gives us conformance of the function near 6 at a much faster rate than this one, which doesn't do a very good job near 6, even for large values of capital N. So we'd have to go pretty far out before I'm comfortable with how close that is to x equals 6. So you can see that the usefulness of a power series also depends on the context. But an individual function can have many different power series representations. All right, what about inverse tangent of x? Well, again, there's nothing algebraic that connects it to the form of the geometric series, 1 over 1 minus x, or the form of natural log of 1 plus x. So we're kind of back at square one here. But again, we have directions of calculus we can move, and we know that inverse tangent of x is an antiderivative of a form that looks a lot like the form of the geometric series. So note, inverse tangent of x is an antiderivative of this form right here. Okay, very good. Why don't we write this as 1 over 1 minus negative x squared. We have the dx there. And we can write this as the sum of n equals 0 to infinity of negative 1 to the n, x to the 2n, dx. All right, so let's write out the terms for our integral here. So this is equal to the integral of the terms of this thing. Well, that would be 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 minus etc. dx. So now let's integrate each of these terms. So we're going to get that constant plus x minus 1/3 x cubed plus 1/5 x to the 5 minus 1/7 x to the 7, etc. Okay, so again, this is what inverse tangent of x is equal to, but in this case we need to determine the value of c because it's not arbitrary. There's a specific c value here. So again, we will choose a specific x value to plug in, and we're going to choose the center of the series. We know that term now. We're going to plug in whatever we would let x equal that would basically clear out all the terms of the series. In this case, the center is 0, so we're going to let x equal 0. Okay, so on the left we have inverse tangent of 0, which is 0. And on the right we have c plus 0 minus 0 plus 0 minus 0, etc. So of course we see that c is equal to 0. And our conclusion is that inverse tangent of x is equal to simply this. Okay, and writing this in sigma notation, we're going to get this form. Okay, and we can work out the interval of convergence here, which is -1 to 1. Again, we're including the 1, but not the -1. So we can kind of think of this as now our third bridge from the universe of functions to the universe of power series. And if we have inverse tangents that we need to deal with in future examples, we can springboard off of this particular result right here. So before going on, we are very close to a really neat fact. It would be remiss if we didn't acknowledge this fact here. So let's just take a quick peek at it. So let's just note that pi is equal to 4 times the inverse tangent of 1. Okay, that's because inverse tangent of 1 is, of course, pi over 4. And that means that we can write pi as 4 times this series, where x is replaced by 1. So we could write 1 to the 2n plus 1, but that's kind of silly because 1 raised to anything is just 1. So why don't we just write that as 1 over 2n plus 1. And in fact, we can distribute the 4 right there like that. So pi is the sum of this particular alternating series. Or term by term, you could write this as 4 minus 4/3 plus 4/5 minus 4/7 plus 4/9, etc. And in fact, if you take the infinite sum of this series, you get pi. So this is a series representation for pi. However, the convergence is very, very slow, which means you have to go many terms out before you get a number that's kind of close to pi in any sort of reasonable way. So this is not a way that we would calculate pi, but it's a way we can calculate pi. Okay, one powerful benefit of power series is that it allows us to work out very difficult or even impossible integrals. Now, this particular integral is not actually impossible. You can actually work this out using the techniques of integration from this course. However, it's a very challenging integral. But we're going to dispatch it using power series. So let's do that. Okay, so the first thing we want is the power series for inverse tangent of x squared. Well, we know what the power series for inverse tangent of x looks like. So let's just replace x with x squared in that power series. So that's going to give us x to the 4n plus 2 over 2n plus 1. Okay, very good. This is what we have to integrate now. Now, again, we could write out the terms of this series and then integrate the individual terms, and then with what we have, rewrite that in terms of a sigma. And that closely resembles what we've been doing in a few previous examples. But what we have not done yet is integrate within the sigma notation, so let's actually just do that for once on this example. So we're going to integrate these terms. Again, it's only the x that gets integrated. So everything else is pretty much going to stay the same. So how do we integrate x to stuff? Well, we add 1 to that stuff. So this is going to be, instead of 4n plus 2, it'll be an exponent of 4n plus 3. But we're also going to be dividing by that 4n plus 3. And of course, we have already a factor below of 2n plus 1. This would be almost our final answer, but we do need to add a constant. It's not a very nice convention to have a sigma series and then followed by plus stuff. So I'm going to do what's fairly normal in this case, which is to put the constant in front. And there we are. That's our final answer for the antiderivative of inverse tangent of x squared. As a follow-up, suppose we were given bounds. Well, we know how to handle this because we know the antiderivative of inverse tangent of x squared is this ugly thing. And of course, we're just going to plug in x equals 0 and x equal 1 and do the subtraction. When we plug x equal 1 in there, we're going to get 1 raised to the 4n plus 3. But again, 1 raised to anything is always 1, right? So we can just write this as 1 over 4n plus 3, 2n plus 1. And when we subtract the 0 plugged in, we're actually going to get 0 in every single term. So we don't even need to acknowledge that. And this series here, which is an absolutely convergent series, whatever the sum of that series is exactly the area under this particular curve from 0 to 1. If you wanted to approximate that value, you would simply work out however many terms of the series you wanted to get the level of precision that you need. But the exact value is represented by this entire series.